Hello, everyone. It's Dan Sandink from the Institute for Catastrophic Loss Reduction. Thanks very much for joining us on our last Friday forum of the season, our June Friday forum. Our next one won't be until September, so you'll get the summer off. We're very, very happy to have Dr. Scawthorn with us today. He's going to give a very interesting presentation. I'm sure we'll have lots of discussion afterward. It looks like we have a good crowd on the line today. Before we get started, I just wanted to remind everybody how we run these webinars in terms of questions and so on. So we will be taking questions throughout the webinar. And if you've been on our webinars before, you'll know how to do it. You use the question and answer function, which you'll find either on the bottom or top left of your screen, depending on what kind of computer you're using. And please feel free to post your questions throughout the webinar, and then we'll have a discussion at the end. As I mentioned, this is the last presentation of the year. Our next presentation will be in mid-September, so you should watch your inboxes, and Tracy Waddington from our office will be sending the notice likely in August. And if you were on the line earlier, you would have seen the notice that we posted for our friends at Aon for their pub night that's happening as part of the Pride festivities in Toronto. So they have an event on Thursday, June 21st at Grace O'Malley's in downtown Toronto. If you happen to be in the area, maybe if possible, we'll put that up at the end of the webinar again with Tracy's help. And with that, a very quick introduction to Dr. Scott Thor. He's one of our presenters who probably needs no introduction. I'm sure many people on the line will be familiar with his work. So Dr. Charles Scawthorn was a professor and head of the Infrastructure Risk Management Laboratory at Kyoto University. He's currently a visiting researcher at the University of California at Berkeley. He's done quite a bit of work on natural hazard risk for the insurance industry, including some work for ICLR. A number of years ago, he completed the paper that we have as part of our paper series on fire following earthquake in the lower mainland of British Columbia. So again, we're very happy to have Dr. Scawthorn with us today. And with that, I will pass it to Charles.
Well, Dan, thanks very much. And everyone online today, good day. Ladies and gentlemen, it's my pleasure to speak to you on ICLR's, the Institute's webinar. And before I go any further, let me just say that I've had many projects and I have many friends in Canada. And while I'm speaking to you from the United States, let me just say that I think all Americans cherish our relationship and our friendship, despite what the occasional hiccup now and then. Let me continue then. This is the notice you received for the talk today, and in order to fulfill the promises made in that presentation, the outline of my talk will be, first I'm going to spend a slide or two letting you know who I am. I think Dan was too generous, so I'll just give you a little background on my company and myself. Then the conflagrations, I'm going to get into definitions, what are they? Then the main talk has basically two parts. Fundamentally, wildland-urban interface, or what are called WUI fires, so somewhat rural area, and of course Canada has many of these, Fort McMurray being the most egregious example in that. And I'll go through the background, the modeling, the benefits of complying with a WUI mitigation or a code, and then one slide on the relevance for Canada. Then urban conflagrations. I'm really going to focus on the problem of fire following earthquake, which is severe in the western United States and western Canada, although you'll see that it has the potential even in eastern parts of Canada, eastern North America. I'll go through the background, the modeling, the codes. That part of the talk will be very brief because there are no codes with regard to this problem, and the relevance again for Canada. And then I'll be closing, and then we'll have Q&A, which I look forward to your questions and our dialogue. By way of introduction, SPA Risk is simply two people, myself and my partner, Keith Porter, who's a research professor at the University of Colorado at Boulder. You can learn more about us at sparisk.com. With regard to myself, this is my education, my professional career. I'm going through this very quickly, I know, but you'll be able to download a copy of this presentation later, so you can dwell on this if you wish. I was a professor in Japan, visiting researcher at Stanford, following my retirement from the Japanese University, visiting researcher at Stanford, UC Berkeley, also in Tokyo and Beijing. And as Dan mentioned, I've done a lot of different work. I am a structural engineer, and this is just one of the structures that I've worked on. This is the Arecibo Radio Observatory in Puerto Rico. It's a unique structure. That's why I have a picture of it. And I have lots of publications, particularly on fire following earthquake, but also done a lot of work for the insurance industry. And this last cover I've put up here, the California earthquake risk, may be of interest to you. It was the LMA, the Lloyd's Market Association, brought about 50 of their underwriters to California a few years ago, and Keith Porter and I spent a week in a seminar with them, classroom lectures, and then going out and showing them the earthquake risk in California. And this is the report that they wrote on it afterwards. I think you can download that from the LMA website. It's pretty. They wrote it. It's pretty interesting, I think. So, moving into our topic now, conflagrations. What are they? Well, the dictionary defines conflagrations as an extensive fire which destroys a great deal of land or property, which is pretty broad definition. The insurance industry sometimes defines it as simply any fire greater than $1 million. And a fire something like this, which is one we had in San Francisco about 2 years ago. This was just, as you can see, a building under construction, a city block in size, and strained the resources of the San Francisco Fire Department simply to control this one blaze. Alternatively, this is Grenfell Towers in London. Terrible tragedy, and by some people's definition, this would be classified, certainly a disaster, no doubt about that, but they would classify this as a conflagration. But this is not what I'm speaking about. I'm not talking about a specific building fire here. What I'm talking about is this kind of event, such as we saw in 1906 in San Francisco, or such as you saw at Fort McMurray several years ago. I'm talking about the kind of event, the kind of fire that spans the horizon. Relatively infrequent, but when it happens, terrible, massive destruction, and great impact on the insurance industry. So, now talking about the WUI fires. How do we define WUI? Well, there are basically two definitions. Actually, the I in WUI can be the wildland-urban interface or the intermix. And the interface is where the houses meet the wildland, and the intermix is where the houses mingle with the wildland. So there's a transition zone. Sometimes it's sharply defined. Sometimes it's there's a broader transition zone. And there's technical definition is shown down here in terms of the density of houses and sort of vegetation and so on and so forth. But here is literally you can see what we're looking at. As a matter of fact, I'm speaking to you right now from this location. This is the Berkeley, and this is the wildland, actually a large natural reserve. And then we have, you can see here, an interface, an intermix area, and then you get into the flatlands of the East Bay of San Francisco, East Bay region of San Francisco, and it's all urban, highly urbanized area. And by the way, not only is this the WUI area, which will be the first part of my talk, but I'll be going to be talking about fire following earthquake afterwards. I should mention before I get to that, this area was the site, and this is a photograph and a headline in 1991 of the largest financial WUI fire, financial loss WUI fire in history, up until Fort McMurray later, and then the events of 2017 in California. That was the East Bay Hills, 1991 East Bay Hills fire, in which in this neighborhood we lost 3,800 structures in about 12-hour period. So the WUI, and it was about a $3 or $4 billion economic loss. So the WUI events are highly relevant. But as I started to say, not only is this an area for the WUI risk, but regarding the second part of my talk on fire following earthquake, the Hayward Fault runs literally right through this area here. I'm sitting only about 400 meters from the Hayward Fault. And if that happens, of course, we're going to have a lot of unhappy people scattered throughout the area. Okay, so these events, these WUI fires, are truly massive. This is San Diego in 2003, and it was only one of the 2003 fire siege that affected Southern California in that year. Just massive losses everywhere, fires of this size. In 2017, we had the Northern and Southern California fire sieges. And you can see here, this is the Northern California set of fires. And in 48 hours in October of 2017, we had 172 wildfires break out. It was hot, dry weather conditions. Of these 172 ignitions, 18 of them grew into large, fast-moving conflagrations, and 9,000 structures were destroyed. 44 people lost their lives. By reference, by the way, San Francisco is down here at the lower part of the screen. Then, a month or two later, we had Southern California, these almost the same sort of situation. 122 wildfires, 1,300 structures destroyed, 2 people lost their lives, and then we had afterwards debris flows, which I'll speak to in a moment. So WUI fires are a large and growing hazard in the United States. There are 220 million acres of wildland-urban interface or intermix within the United States. Within that area, there are 46 million single-family homes, several 100,000 businesses, and about 120 million people living there, or about a third of the nation. 14% of the available WUI fires in the western United States have been developed, and 86 remain available. So people are going to continue to move into these areas. Nationally, across the United States, the mix is about 30% developed and 70% remaining to be developed. In these areas, about 38,000 homes have been lost since 2000. And this doesn't include the numbers from 2017, where you could add another 10,000. So actually, up until today, from 2000 to today, we've lost on the order of 50,000 homes in the WUI fires. The financial losses through 2009 were totaled to be $14 billion. The 2017 events are probably approaching $10 billion, by the way. So we're talking big bucks here. And that's only the actual property and physical losses of property and BI. There's also the cost of firefighting, just having crews stand around, all the equipment, all the infrastructure, and so on. And those exceed, those preparations and so on, and then the emergency expenditures exceed $4.7 billion per year. So these are, again, big numbers. And there are other kinds of loss, like, for example, mental trauma and so on, that are not generally accounted for. And this all comes from the International Codes Council WUI fact sheet from 2013. So here's a map of WUI fires that between 1984 and 2014. And if we zoom in, we can see for example, for the Los Angeles area, I mean, literally anything that's been available in the WUI intermix area has burned, and often more than once. So and this is the kind of things we're talking about. This is Santa Monica fire of a couple of years ago. Now, to quantify this, to look at this, and the work I'm going to be presenting to you was just published and released in February of this year. It was a study conducted by the National Institute of Building Sciences. It's my work as part of this study. And it was sponsored by FEMA, Federal Emergency Management Agency. And not only FEMA was the main sponsor, but the International Codes Council, NFPA, American Institute of Architects, and so on, all co-sponsored this study. What this did was it looked at the benefits of mitigation for a wide variety of natural hazards. And actually, this was an update. And by the way, it's the interim 2017 interim report results I'll be presenting to you, because we're still working on this. We presented phase 1 of. Sorry, let me go back to the history a little bit. This study actually had its beginnings in about the year 2000, when Congress asked FEMA to quantify the benefits of mitigation. Congress said to FEMA, you know, we're paying a lot of money every year for these disasters, and also we're paying a lot afterwards to mitigate these disasters. Is that money well spent? What's the benefit cost? So FEMA worked with the National Institute of Building Sciences, and in 2003, they released these results that showed, for example, that for flooding, $1 spent on mitigating flooding saved $5 in losses. For hurricane surge, wind, and so on, the cost-benefit ratios were on these orders, 7 to 1, 5, and so on. And actually, there's a sort of a typo here because those are those studies. And then 10 years later, FEMA said to National Institute of Building Sciences, it's time for an update of this. Why don't you redo the study and look even more broadly? So the NIBS team, which I was a member of, looked at it also, and we looked at it even in more detail. And we looked at all federally funded projects, and we found the ratio had gone from 4 to 1 to 6 to 1. And we looked at, if you went beyond code requirements, what the benefits would be. And for wildland-urban interface, this is the breakdown, and this is the map of where the benefit cost ratios, of the variation in benefit cost ratios. And of course, you can see in large parts of the United States where WUI is not a problem, WUI fires are not a problem, the benefit cost ratio is nil. But in the areas where you do have the potential for large wildland-urban interface fires, which is not only the western United States, but also particularly in Florida, a little bit in the New Jersey, New York area, and then also in the Tennessee, Kentucky area, the benefit cost ratio, the benefits of engaging in mitigation can be as high as, on average, 6 to 1. Actually, it goes even higher. Now, before I go further, this study was overseen by a committee, and I just mentioned it because I want to appreciate their efforts. Mark Finney, Dr. Mark Finney, who's a research scientist and leads the Fire Sciences Laboratory of the U.S. Forest Service in Missoula, leading expert in this area. Kim Zagaris, who's chief of California's Office of Emergency Services Fire and Rescue. This is Kim here speaking. Jack Cohen, another internationally renowned research scientist from the Fire Sciences Laboratory, and Rob Plonsky here. You can see him playing with fire here, or here's the fellow. He's a fire protection engineer at the Department of Energy. They vetted this study and the results, so I appreciate their efforts. Now, the analytical approach for doing this is similar to the analytical approach for looking at the damages and the benefits, benefit cost ratio for any kind of a natural hazard. We start with the hazard, which in this case is the WUI fire. It could also be, if we were looking at an earthquake or flood, it's the same, just you change the hazard. You then look at the exposure. Of who's exposed to that. You take the vulnerability curves, the risk calculations, and you go through a calculation to quantify the expected annual loss. You sum that over all the potential future years, and you'll come up with an estimate of the damage and financial loss that would that accrue due to this hazard and this exposure. That's on the damage side. You can do this under an unmitigated condition, under a mitigated condition. The difference between the two is the benefit of the mitigation. That becomes your benefit. You divide that by the cost of the mitigation, and that gives you your benefit cost ratio. That's the basic framework within which this was done. Now, in quantifying the hazard, the heavy lifting for this study had been done by the U.S. Forest Service. They've done a number of studies, and again, this work was led by Mark Finney and his team at the U.S. Forest Service, really excellent body of work that we were able to build on. They've developed the entire databases and framework for estimating losses due to WUI fire. You can see these are some of their reports, and this is a mapping of the wildland-urban interface within the conterminous, the 48 states of the United States. And you can drill down on this, and this is a state of Virginia, for example, and I chose that rather than California, which would have been all red, just to show that even in a place like Virginia, you can see that a large fraction of the state is either interface, which is yellow, which is not so much here, or intermix. In the deciduous forests of the eastern United States, virtually all houses outside of all buildings outside of intensely urbanized areas are within the intermix. So you can see a large part of the state is in the intermix area, and this gives the breakdown down here. And these, again, if you go to the Northern Research Station's website, you can download these kinds of maps if you're interested. And this shows, again, for Virginia, what how the breakdown was, and about half the housing units are in the WUI exposure, about half the population, and so on. And this is the state of Virginia, where you wouldn't expect it. Okay, this is another map of the San Francisco Bay Area, which shows the same sort of area. The yellow is the yellow and orange are the WUI areas, interface and intermix. And again, I showed you an aerial photograph before of this area, and this is the outline of the 1991 fire of this area here, where 3,800 houses were destroyed in about 12 hours. These other red outlines are other fires, WUI fires that have historically occurred, sometimes 20, 30 years ago, and so on. So even in an area like San Francisco, you can see that there's significant exposure here. And again, later I'll be talking about the Hayward Fault, which runs through this area, and the potential fires that can occur in the urbanized area here. So, and this is just a zoom in to show how the mapping here. And you can see very few structures in this area, and then you have the intermix area, a lot of vegetation and a lot of structures. So this is another schema for doing the analysis. You take your highly valued resources and assets, you take your burn probability, combine them through what the Forest Service terms response functions. More broadly in the insurance industry, we would call these vulnerability functions, and you combine these together and you get your the wildfire risk. And these show, this is again the same mapping showing the burn probabilities as mapped by the U.S. Forest Service. Now, the burn probabilities are on a gridded basis for the entire United States, the probability of an ignition occurring within that grid cell. And this is largely empirically based. It's actually a hybrid model. Some of the data comes from empiricism of simply the ignition rates in previous years. And then some of it comes from the types of fuel that are there, types of wildland growth, vegetation, rainfall, slope, wind, and many other factors. With these combined, you come up with the probability of an ignition occurring within that grid. And this shows, again, the more detail within that grid. You can then look at the fire intensity levels and so on. This shows the residential exposures that as compiled by them in that area. And then to look at the mitigation then, we looked at complying with the International Wildland-Urban Interface Code as published by the ICC, the International Code Council. This is required for new construction in California. It's required to build, if you're in the WUI area, you must comply with this code. And in other states, case by case, it's also required. The code, this is the table of contents, and the relevant areas of interest are, they define the wildland interface or WUI areas. They define the special building construction requirements, which I'll describe in a moment, and the fire protection requirements, and so on, including access and other things like that. So if you're going to have new construction, you must comply with this code, and it defines where you must comply with it, and if you're in that area, what you must do, and what the fire department or the municipality must also do. Now, the structural requirements are encapsulated in this diagram, and they include a number of things. For the structure itself, you would have you would require a non-combustible roof. a fire-rated cladding, fire-rated glazing, protection of soffits and other aspects of the structure, so that if embers or a flame approaches the structure, it is not easily ignitable. But another key part of it is to keep fuel away from the structure, and that includes moving storage sheds and wood piles and other things further away from the structure, not allowing them to be there, and also creating what is called a defensible space around the structure. And this, depending upon the degree of fire hazard, this defensible space is an area 30 feet, 50, 70, or 100 feet around the structure, in which the vegetation must be mowed away from the structure. Coniferous trees must be thinned or pruned, and so on, so that you reduce the fire intensity that would affect the structure. As I mentioned, also fire protection requirements, you must have an accessible driveway and so on. I might mention also that the Institute for Catastrophic Loss Reduction has adopted these recommendations, and they've made it part of their Fire Smart program. And this diagram here, which is taken from the ICLR's publication, outlines very much exactly the same practices. So you have the same practices in Canada. However, as far as I can see, the requirements for complying with this, I'm unclear as to whether this is required to comply in California or simply a series of recommendations. I will say that in the United States, in California and a number of other states, Colorado, particularly the Western United States, this is mandatory. I described the methodology before. What we did was we want to calculate the benefit cost ratios given WUI fire protection. And what we did for the study was we took 4 selected areas, 4 selected counties across the United States. I'll show you those in a moment. We defined an index building, which is a single-family wood frame dwelling. We took that dwelling under as-is conditions without compliance with the WUI Code, assuming no mitigation or compliance with the code, and then we looked at it complying with the code. So these were the unmitigated and the mitigated conditions. We calculated the benefit as the average annual loss, avoided losses, including property losses, additional living expenses, and every other loss that we could conceive of that could be financially quantified, including what we termed PTSD, post-traumatic stress disorder. In other words, the mental anguish. There's data now that's emerged as if people suffer mental anguish or PTSD following a disaster, what it would cost to treat them for this. So you can quantify the cost of that. It may not be insured, but you can quantify what that social cost is. So we did that. We also took into account mortality and morbidity. In other words, cost of loss of human life and cost of injuries, all of those avoided losses, if mitigation occurred, were quantified. We then took into account the cost of complying with the code, which is non-trivial. Putting on the different structural features of the roof and the cladding and so on adds some cost to the structure, but the largest cost, surprisingly, that we found was the cost of continued vegetation clearance year after year after year. It was a little bit surprising, but that's the largest cost of the entire compliance. And as I mentioned earlier, the benefit cost ratio is simply the benefit divided by this cost. So the 4 counties we looked at are shown here. We looked at Los Angeles County as an example of an extremely high value, high risk area. Alameda County, which is where I'm sitting, is where Berkeley and Oakland are in the East Bay of San Francisco Bay Area. We also looked at, because again, it's comparably high value, high risk area. We looked at Ada County, Idaho, which is probably the most heavily exposed to WUI risk in the United States, very high risk area. And then we looked in the eastern United States at Atlantic County, New Jersey, an area that has some WUI exposure. So by looking at these four, we felt we captured the spectrum of very high exposure, very high risk, down to moderate exposure, moderate risk. This shows the populations of those four counties. Los Angeles County is 10 million, and the Atlantic County, New Jersey is only 250,000 people, and so on. The specific measures, I've already outlined those. This is the same diagram I showed you before, so I won't go into that again. This, however, shows this more specifically what those requirements are. Depending upon whether you're in an ignition risk area 1, 2, or 3, risk area 1 being the highest ignition risk area, the roofing is required to be a Class A non-combustible, Class B, or Class C. And actually, while there are distinctions here, from a practical point of view, there really isn't much difference between a Class A, B, and C non-combustible roof. And any builder would simply, if required to do this, would put a Class A roof. And that's simply your fiberglass shingle type of roof. They would put that on because compared to the labor costs, the material differential costs are negligible. Roof valleys need to be flashed per the code. Eaves and soffits would have to have a 1 hour rated covering for ignition risk area 1, and no requirement in ignition risk area 3. Gutters and downspouts need to be non-combustible. Exterior walls would have to be 1 hour rated for these risk areas, or no requirement in 3. Underfloor areas, meaning protection of the basement area and under decks and so on, need to be enclosed with a rated enclosure. Appendices and projections, again, decks and so on. Exterior glazing would have to have a 20-minute rating, exterior doors and so on. And in ignition risk area 1, you want an automatic sprinkler system, but it's not required in 2 or 3. The defensible areas, the defensible spaces around the building are in moderate WUI risk areas would be 30 feet, and in extreme hazard areas going up to 100 feet or about 30 meters. So 10 meters to 30 meters in those cases. This is the mapping of those burn areas. I've already mentioned it. You can see, and these are we looked at again, LA, Alameda County, Ada County, and over here Atlantic County in New Jersey. These are the mapping of those 4 areas. And then flame intensity, if ignition occurs, how intense is the fire? And this is based on the type of fuels and also the wind environment and so on. And this has been, again, this is worked by the U.S. Forest Service, so this has been all mapped, so we're able to take that into account. And this actually defines what the flame intensities are, and you go classes from 1 to 6, and at class 6, the flame lengths are on the order of 12 feet or more. So these are the kinds of flame intensities that you saw in Fort McMurray, or we saw in California in 2017. This is really the kinds of fires that you really can't fight these. You just need to run for your life. FLI 1 is 0 to 2 feet, and these are possible to fight these, and so on. So this is a definition of your flame intensity lengths. The exposure, these are the actual values by for each county. This is all documented. I had 47,000 different cells for which the analysis was done. I won't go into any great detail on that. Just simply this is a very detailed, data-intensive exercise. For the vulnerability functions, again, what the Forest Service calls response functions, it shows as a function of flame intensity level, the fraction of the value that would be lost for different kinds of construction. So, for example, this is the property loss due to a structure. Well, let's start with the red line. This is the fraction of the loss that would occur to a single-family home exposed to these flame intensity levels that does not comply with the code and for which there is no fire suppression. So you can see even at, say, flame intensity level 2, which is a flame length of 2 to 4 feet, but no defensible space around the structure, it's probably about 70% likely that, or about on average, 70% of the structural value would be lost. And very quickly, you get up to where it's just a total loss of the structure. However, if they're complying with the code, even if there's no suppression, because of the defensible space, the fraction of the value, or another way to look at it, the average, the probability of the loss occurring, drops dramatically from, for example, at flame intensity level 2, from 70% down to about 10%. So the loss is dramatic. The dotted lines are with suppression, and if you've complied with the code and there is a defensible space around the structure, it enables the firefighters to really protect that structure. So the losses go unless you're out at flame intensities 5 and 6, where you've got 10 and 12 foot flame lengths. It's very little. It's very unlikely the structure is going to be heavily damaged at all, if you've complied with the code and have the defensible space. If you don't have the defensible space, then pretty likely, even with suppression, the firefighters aren't going to be able to save the structure. So these are the vulnerability functions we used. And to some extent, this was based on U.S. Forest Service work, and to some extent on the work we did within the project itself. For those actuaries who are online and more mathematically oriented, you see here the actual computations, and this looks like a very daunting equation, but actually it's pretty straightforward. It simply says the loss is the summation over all these factors. So in effect, you're just adding up all the different possibilities and multiplied by their probabilities or their frequencies of what would occur. So this is just for those who want to know whether this was done with some detail or not. Yes, it was. So this shows then the benefit cost ratios per housing unit for LA County. These are our final calculations, and it shows the mapping of that. So you can see that areas that are mapped blue or say green have benefit cost ratios on the order of anywhere from 1 to greater than 10. These are our results. Given all these calculations, it shows that basically anywhere you have wildland-urban interface risk in Los Angeles County, it is cost beneficial, at least even money, but often $5 or $10 return for every dollar you invest to mitigate wildland-urban interface fire. In other words, to comply with the WUI Code. And this, by the way, shows the red hatching is the mapping of the brush zones in California by the California Office of Emergency Services. So you can see that the mapping of the brush zones pretty much is congruent with the benefit cost ratios. So in this sense, the requirements of the brush zones make perfect financial sense. Should come as no surprise, but this validates that. And I could show you maps for the other counties, but taking all that data, we came up with, for those 4 counties, about 10% of the census blocks examined, excluding purely urban census blocks, had benefit cost ratios greater than 2 to 1. And this is the actual distribution. The largest benefit cost ratio was about 12.6. There were 10 census blocks that had benefit cost ratios of 11, on average 11.4. The 100th, in a frequency distribution, the 100th census block had a BCR of 9.5, the 1,000th 6.6, the 5,000th 2.1, and so on. So using this distribution, then we could then do a mapping. We then extrapolated this to the rest of the United States using their burn ratios, their exposures, the flame intensity levels, and so on. And we mapped every county in the United States. And on average, we found that where there is a wildland-urban interface mapped exposure, that the BCR on average for all kinds of construction was about 4.1. The cost of complying this for these structures that are exposed in this area will be about $800 million, and the total benefits for 1 year of implementation would be about $3 billion. That gives you your 4 to 1. And the benefits are broken down in this area. The property losses of the 3.3 billion, about 70% were due to property loss. Casualties, that's mortality, morbidity, were about 5%. Additional living expenses were on the order of 3%. Indirect BI was about 2%, and about 20% were insurance savings. By the way, this is probably another way of saying that if you comply with the WUI Building Code, in theory, your insurance premium should be reduced by about 20% for fire, the fire portion of that code. The actuaries would probably say, well, wait a minute, let's sharpen our pencils here. And they'd be correct to some extent. I'm generalizing. But anyway, this is the mapping here. And as you can see, this is of great value because it informs local governments who are considering mandating, state or local governments considering mandating compliance with WUI Code. They can look at this map and they can say, well, if we're here in Iowa, we don't need that. But if we're down here, say in Florida, yes, we do. This is in California, but yes, we have wildland fire problem, and this shows that it's very cost beneficial to comply with the code. Or even, for example, in a place like Kentucky and West Virginia, which may come as a surprise to them, and so on. So now, I wanted to, and that is basically the work that was done for the National Institute of Building Sciences and for FEMA on the quantification of benefit cost ratios for wildland-urban interface code compliance. I wanted to mention one other aspect of this that emerged after, just as we were completing the study, and that is the post-WUI fire debris flow problem. As I mentioned earlier, in Northern California, we had what the Fire Service termed the 2017 fire siege, with about almost 9,000 structures and 44 lives lost in October 2017. In December, in the Santa Barbara area, and in Southern California in general, particularly in Santa Barbara area, we had, again, about 1,500 structures that were lost and 2 lives were lost. But following that, they had intense rains, and the topography, the relief in Southern California is steeper than it was in the areas in the Coast Range in Northern California, and they had severe debris flow in city of Santa Barbara and nearby cities. And this is a photograph of rescuing a victim from one of those debris flows. It's a terrible situation, and this shows the Santa Barbara area and the post-fire debris flow hazards. Now, the California U.S. Geological Survey and the California Geological Survey have a very responsive program that if there is a wildland fire, within a day or two, they can map the probability of having a debris flow based on topography and so on, posited on having a certain degree of rainfall. So in other words, what this is a map that was generated for this area following the December fires by the USGS. And it says that if you have a certain intensity of rainfall, then the probability of having a debris flow in these different catchments is denoted by the color here. So you can see virtually certain in certain high relief, very hilly areas. And this is based on the type of soil. It's based primarily, of course, on the steepness of the slope, but they also take into account the type of soil, the intensity of the fire that occurred, the vegetation, and so on. So very detailed, very responsive, very valuable, and was validated, unfortunately, when indeed they did have that rainfall and we had the debris flows here. This mapping, however, is relatively broad in the sense that it just shows the degree within a catchment. And if you actually look at the catchment, of course, if you're up at the top upper elevations of that catchment, the debris flow hazard is relatively minor. And as you go down into the notch of the valley, so to speak, the notch of the V of the valley, closer to what's called the Thalweg, which is the lowest point within any particular gully or valley, then the debris flow material, the depth and so on, are going to increase. So your hazard is much higher here. Now, this kind of detail is not captured here. For example, the mapping of this particular catchment maps the whole catchment, and this more detail here is something that we've been doing recently to map this so that we can actually define more specifically, precisely where the debris flow hazard exists. And and this work is being done for a client who's interested in knowing more specifically where their assets are at risk. So this is something that I think of interest to everyone. So in summary, for part one of my talk, the wildland-urban interface, we modeled it for the entire United States. We calculated benefit-cost ratios for 4 case studies. We extrapolated those results to the entire United States. We found BCRs ranging, of course, from 0 to on the order of 12, with an average for BCRs greater than 1 of an average of 4. And we also have done some post-WUI fire debris modeling. So what's the relevance of this for Canada? Well, it comes as no surprise. There's quite a bit of wildland WUI areas in Canada. And this is a paper by people at the Natural Resources of Canada Agency, just published in 2017, which for the first time produced a national map of WUI in Canada. And Canada has 32 million hectares of WUI, about 3.8% of the total national land area. And you got a large land area, so 3.8% is large, and so on. Again, just published in December, a few months ago. This shows them this is from their paper. It shows the mapping. WUI is ubiquitous across Canada, and every year you have about 7,000 wildland fires burning more than 2 million hectares. This shows the mapping, and it shows the non-interface. Green are the non-interface areas, and red are the interface areas. So you can see that you have a problem comparable to what we have in the United States. Maybe not quite the same scale, but smaller population to some extent, but still a significant problem. And how is Canada responding to this? Well, I don't know everything that's going on in Canada, obviously, but this was a few years ago where building code changes for wildfire-prone areas in Slave Lake, Alberta. A federal commission rejected the proposals to change Canada's national construction codes to better protect communities. So going back to ICLR's guidelines for defensible space and so on, which are very similar to what we do in the United States, at least as of 2011, there was no consensus to go forward and put this in the codes. Things may have changed, especially after Fort McMurray. I don't know. This is about all I could find. And so this is another report by ICLR showing the risk reduction status of houses, and this is as of 2015. And what ICLR found was that the fire smart solutions, which is what I showed you from their other publication, have been widely adopted by homeowners, by some homeowners, and some, but others and some homeowners very little or none at all. Overall, twice as many wildfire hazard factors received a poor adoption grade. So it sounds like there's a lot more that still could be done in Canada, just like there's a lot more we can do in the United States to improve this problem. So this is the relevance, and some of the kinds of mapping and analysis that I've shown you here may be useful to be done in Canada, particularly to map the benefit-cost ratios, where to identify those areas and to convince legislators and voters where it is cost beneficial to comply with the code so that it becomes mandated. All right, that's what I wanted to say about the WUI fire problem. And again, thanks to the U.S. Forest Service and many other people for helping with our analysis of that. Now I want to talk to urban conflagrations, particularly fire following earthquake, and I'm going to be presenting some results that were just released in April of work that we did for U.S. Geological Survey, again, looking at a magnitude 7 earthquake scenario on the Hayward fault. Now, it's called the Hayward scenario because one night after a little celebration, we were talking and we said, well, this is the Hayward fault, and this is the wired community. This is Silicon Valley. So what happens if things go haywire due to the Hayward fault in the wired community? And we thought that would be a good name. So that's where the Hayward name came from. And as I've shown you the slide already, we know that from 1991 that we certainly have a major fire potential in this area. Now, the Hayward study was part of a series of the U.S. Geological Survey has been done over the last 10 years called SAFER, which is Science Applications for Safer Societies. And the first one of these was the shakeout analysis done in 2008 for the Los Angeles area. You may have heard of that. They've done others looking at winter storm scenarios, tsunami, and then the Hayward. The Hayward, part one, which is the Earth Sciences study, was released in April of 2017 and is available in this report. And then in April of 2018, the engineering aspects or implications, which I'll be presenting to you now, were released here in Berkeley literally on the Hayward fault in April. And that report is also available from the USGS website. The Hayward Fault area, this is the San Francisco Bay Area, is arguably the most urbanized active fault in the United States. And so we have, you can see the urbanized areas with these shades of mauve, I suppose, and the different faults. The San Andreas Fault, which erupted in 1906, which is, however, doesn't run directly through the urbanized area, but rather alongside it, and the Hayward Fault, which literally is a direct hit on the urbanized area right here. There was a lot of work that was done by the earth scientists, the seismologists, and so on at the USGS as the foundation for the engineering analysis. One of the particular aspects that one of the advances that they did was in previous studies of this and other faults, including in the lower mainland of California, of British Columbia, and so on. Generally speaking, median ground motions are used, and recent work has shown that only using median ground motions and not taking into account the uncertainty on these ground motions greatly underestimates the actual losses that could occur. And this is a fault with all the modeling that's done in the insurance industry, actually, and this has just emerged very recently. And so we used physics-based modeling, which looked at actually the variation within the waveform, and you can see the difference in the ground motions that you get, and how just using the median values grossly underestimates the potential for ground shaking. The actual event that we looked at was a magnitude 7 earthquake occurring at specified a time, April the 18th, at 4:18 p.m. With mild wind, no rain, and average temperatures. So in terms of fire spread, this is far from the worst case conditions. The rupture started under Oakland and spread north and south. It's bilateral rupture. 83 kilometers in length, up to 2 meters of fault offset, and so on. This is actually an animation of the rupture occurring. You can see it on the left here, and you can see it coming towards you. This is a picture from, looking from downtown Oakland, and you can see the rupture occurring here. Here comes the first P waves, and the red now coming on the S waves. They're arriving towards you, and this is about 20 seconds into the rupture, and it's now you can see the ground is moving. It's obviously the movement is somewhat magnified, but it sure looks like the waves at sea. And this goes on for a long time. You can see this violent ground shaking is now, we're into 15 seconds of violent ground shaking, now approaching about 20 seconds of violent ground shaking. And this continues, and actually will continue for another 30 seconds. So we got about 50 seconds duration of strong ground shaking occurring at this area. This is a terrible earthquake affecting several million people in the San Francisco Bay Area, and we all have our fingers crossed. This map in the upper left shows the actual fault displacements along the fault, and in the Hayward and Oakland area, we're looking at about 1 to 2 meters of displacement. up in the Berkeley, Richmond areas, 2 or more meters of displacement across the fault. And what that means is that roads and bridges and so on would be sheared by up to 2 meters of displacement. Obviously, this makes them unusable. And another interesting aspect of this study, which has not been done before, was not only to look at the main shock, but to look at the aftershocks. And in most loss estimates, including most modeling done for the insurance industry, aftershocks are neglected. It's assumed all the damage, all the structures that are going to be damaged are damaged in the main shock. And that is actually not only a poor assumption, it's an erroneous assumption, because aftershocks don't occur simply where the main shock occurred. They move around it. And if you want to ask the people in Japan who have been still continuing to sustain aftershocks from the 2011 subduction zone earthquake there, these go on for years. So this map on the right here shows the geographical distribution in plan of the aftershocks, and you can see many of them are occurring off the main shock. And then below that on the in this histogram are shown measured in days after the main shock, the number, the distribution, the number of, and the magnitude of the aftershocks. And you can see that, for example, 30 days after, we're still getting magnitude 6 events. 6 months later, there's a sympathetic rupture of a fault, and we get some more aftershocks and so on. So these go on for 2 years, and so you'll continue to have damage. So the normal earthquake requirement in the earthquake policy of 72 hours will simply be reinstated every 72 hours, and every aftershock will then will cause additional damage. There's another slide that shows it. 12% of the damage occurred from 3 aftershocks of magnitude 6 or greater. 8% from so aftershocks contribute more than 20% of the damage or losses, and so on. Some areas are more damaged by the aftershocks than the main shock. And this analysis was the first time that this was taken into account. And this shows some of the shaking intensity patterns from aftershocks. So now to look at the fire following problem, we start with the ground motions. And again, all of this is documented in this report you can get from the USGS website. So we start with the ground motions. We see the shaking intensities shown here. We then look at the exposure. And we have the exposure is about 7 million people are in the Bay Area, almost 6 billion square feet of floor area. I guess that's about 600 million square meters, roughly, of floor area, and about $1 trillion of total building value at risk. And actually, this is probably an understatement, because this is only structural value, does not include contents, and it's estimated using $200 a square foot, or about $2,000 per square meter for reconstruction costs, and which is low for the Bay Area, although it would be high for other areas. So anyway, that's the numbers that we used. We then looked at the fire service. These are every one of these green dots is a fire station in the Bay Area. California has a very large, well-practiced fire service but still is stretched to its limits by some of these conflagrations and would be overwhelmed by this earthquake. Each one of these cells is an area around each fire station to show the area where that fire engine would respond, and so on. What came out of the study was something that is very interesting, that water really dominates the earthquake risk to society in 2 ways. One, because, as I'll show you in the next slide, their lack of water greatly increases the losses due to fire following earthquake, but also the number of breaks. We're estimating 5,000 to 10,000 breaks in the distribution system in the Bay Area here due to this earthquake would take many, many months to replace. And during that time, economic activity and even just people barely able to survive is greatly impaired. And there's going to be displacement. That means people moving out of the Bay Area, just as we saw them moving out of New Orleans because of this, and that's going to impact the the business, so your business interruption losses are going to be huge. So the water is water is fundamental to life. We all know that, but it certainly jumps out at you in this event. Now, this is actually a mapping for those same response areas for each fire engine of whether water would be available to suppress fires. And red would show that there's less than a 10% likelihood of water being available where there's red, and up to where the blue is where water is available. So you can see along the fault here, where the fault is literally shearing the pipes, but even more broadly just breaking pipes everywhere due to shaking and liquefaction, there's not going to be any water available to fight fires. So all those fire engines are going to be hard-pressed to do anything. And all the mutual aid that comes in is also going to have the same problem. So in analyzing this then, we took into account, first of all, the earthquake damage, the multiple simultaneous ignitions, the fire spread, the water supply and response problems, the communications breakdowns, and the competing demands for fire service resources, meaning search and rescue and saving people's just basic EMT, emergency medical treatment, and so on. The model for doing this is a model that I developed years ago, and some of you may be familiar with this. And it's shown in this diagram. The x-axis here is time, and which begins at the time of the earthquake. The earthquake occurs here at time 0, and the y-axis is just every ignition that would occur: ignition 1, ignition 2, and so on. The ignitions. Now, some of the ignitions, like ignition 1 and ignition 3, occur immediately, within seconds or minutes following the earthquake. But some of the other ignitions, like number 2 and number 6, are delayed. They may be delayed hours. And why are they delayed? Well, it might be chemical reactions that take time to build up the heat. It may be some electrical equipment that, again, power is restored, or batteries and so on take time to, again, build up the heat. In any event, these ignitions occur with this time pattern. For each ignition, there's a pattern here. I'll take looking at number 8. The ignition number 8, for example, between the time the ignition occurs, there is a delay until it is discovered. D stands for discovery. Now and during that time, the red bar means fire growth. The fire is growing. Now, under normal cases, sometimes even without an earthquake, there is a delay, and a fire will grow to be fairly large before it's discovered. But usually, it's discovered pretty fast, and people report it. They pick up the phone and they call the fire department. But after the earthquake, there will be another delay, typically from discovery to the report, because 911 will be totally overwhelmed, and in many cases, the people will literally have to go to the fire station, or the fire fire crew on the fire engine will see the smoke and respond to it in that way. So there'll be a delayed response. And during that time, again, the fire is continuing to grow, and fires grow exponentially. So and then from the time it's reported to the time the fire engine arrives, there will be, of course, some time involved, and often a delay because there's not enough fire engines. And so, but when they get there, then they will start to suppress the fire. And fire growth was shown with the red bar, and fire suppression is shown with this sort of wavy blue line here. So they will start to suppress. So, for example, looking at number 3 here, there was the ignition, there's the discovery, the report, the fire engine arrives, the fire grows, and the width of the bar shows the size of the fire as it's growing. This line here, for example, at number 8, the narrowness of that bar means that one fire engine can suppress that fire. Up here, ignition number 1, when it grows to 2 bars in width or 3 bars in width, that means 2 engines or 3 engines are required to suppress that fire. So ignition number 1 has grown rapidly, even though it was discovered and reported. 3 engines were required to suppress it. They arrived. It took them some time to suppress it. They finally did suppress it, and at that point, those engines can start to be redirected to another fire. And looking at number 4, that one has grown very large. Other engines have responded to other fires. They've suppressed those. They're all responding to fire number 4 now. And the key question is, are they able to suppress it, or will it grow to a conflagration, to literally a conflagration? And that's what the modeling, that's the fundamental thing that we're looking at. Is the fire confined to a few buildings, or is it going to grow to a multi-block conflagration that spans the horizon, so to speak? So to do that, it's a stochastic process to model it. We have to take into account the ignition occurrence and fire spread given the performance of gas and power systems, the water supply given the distribution damage, fire reporting given the saturation of the plain old telephone system, cellular and 911 systems, fire department decision making given the radio chatter and the overwhelmed EOC and many other things, and other demands. In other words, fire following earthquake is very complex, extremely complex process. And I've been working on it for 40 years, and a number of other researchers have worked on it too. And I refer you to a book that I led the development of, published by the American Society of Civil Engineers and NFPA, shown here. You can get that from ASCE. That documents how all of this is done. The ignition models that we used for the Hayward study are work that I did for the National Institute of Building Sciences and FEMA a few years ago, and also work done by Professor Rachel Davidson at the MCER and the University of Delaware. This compares the two models and basically just shows that two models are pretty similar. So we have a mapping of the ignitions, again, using the same fire response areas. You can see that whereas bright red, you got more than five ignitions per fire engine in that area. And don't forget, there's no water there. Now, moving of the water is an issue. People say, oh, well, just the fire engine can, if there's no water at the hydrants, they can just run down to the nearest swimming pool or creek or San Francisco Bay. I mean, it was ironic in 1906 that San Francisco burned down for lack of water, even though it's surrounded on three sides by the largest body of water on Earth. But moving that water, they weren't able to do it in 1906, and they're still not able to do it, quite frankly. And I say that with some confidence because as a visiting researcher at the University of California, I did a study of the ability of water supply reliability in regard to fire following earthquakes, sponsored by California Seismic Safety Commission. I looked at all the urban fire departments in the state of California and all the water departments. And again, you can go to the California Seismic Safety Commission website and download this report. And the inescapable conclusion was that there will be little or no water after an earthquake because they cannot move the water. It's not well planned, with very few exceptions. San Francisco, Oakland, and Berkeley are a few of the fire departments who have practiced this and have the equipment to do it. But Los Angeles, for example, is not really equipped to do this. So, and this is further demonstrated, by the way. In 2014, I ran a workshop for all the fire departments in the Bay Area. This is, again, Chief Zagaris from Chief of OES Fire and Rescue Group. And these are fire officers from all the fire departments in the Bay Area. And for the first time, I got them to get together to do an exercise to start moving water. It's the first time they've ever done this. And they haven't done it again since, by the way. So this is, but I could, this was an effort I was trying to get them to, as a result of that study, to work on this problem. So the findings were, bottom line for the Hayward study, we're going to have hundreds of large fires. Actually, it's about 600 large fires. There's going to be much damage to the buried water supply. You're going to have dry hydrants. You're going to have losses of hundreds of lives, tens of thousands of buildings lost due to fire, $16 billion in coverage A, using insurance policy terminology, losses, which is fully insured, minus negligible deductibles, $16 billion in direct property structural losses, and you can almost double that to include coverage B, C, and D losses. So in other words, additional living expenses, contents, and so on. There are many opportunities for mitigating this problem. Post-earthquake supply of water for firefighting is the primary one of which, and as I just showed you in that previous slide, the ability to move the water is the key issue. I think a California statewide emergency water supply system was needed. I've been recommending and working towards this goal. Matter of fact, we're having a workshop in August with all the fire and water agencies in the Bay Area towards that goal. In California, we should have mandated gas shutoff valves and seismic shutoff meters in densely built areas. And these same recommendations, by the way, would apply to the lower mainland of British Columbia and other certain selected other areas, for example, possibly parts of Quebec in Canada. On aggressive seismic retrofitting, for example, on the sale of a house and so on, and continued development of citizen emergency response teams. So all of these results are available from the USGS if you just Google USGS Hayward, you'll come to these two reports and you can download them. And this is the Earth Science one, which if you're not a seismologist is probably of little interest to you. But this is the engineering implications, which actually insurers will find of great interest. And you'll see on the cover, by the way, this is a photograph from the 1989 Loma Prieta earthquake, the fire following the Loma Prieta earthquake. Relevance for Canada. Well, you have earthquakes in Canada, just like we have them in the United States. They're dominated by the plate boundaries, particularly in the lower mainland on the west here. But in the Quebec and the St. Lawrence Valley, it exists also. Of course, you have them up north, but the exposure there is relatively small. So we'll focus on, particularly in lower mainland. In 2001, I did this study for Institute of Catastrophic Loss Reduction, assessment of the fire due to fire following earthquake. Some of you may be familiar with that. 17 years have gone by and much has changed. We have a better understanding of the hazard, for example, that aftershocks are going to occur, and particularly for the scenario event that was done for this study. The 2011 Japanese earthquake and the tsunami that followed it are a mirror image of the Cascadia event that was studied in this event. And the aftershocks in Japan have gone on for years, and it's only fair to say we'll probably have aftershocks going on for years that will affect the Puget Sound and lower mainland areas. There's greater exposure, of course, 17 years of growth, and heavens, Vancouver is just, the amount of construction in Vancouver is huge. There's better data on exposures. In general, and I'll show you that in a moment. This, by the way, was the scenario that we looked at. We looked at several different scenarios. We looked at this is the Cascadia event, and these are the historic events that have occurred in that area. This is the actual Cascadia event that we looked at. And with regard to exposures, before we had broad information on exposures, now we have literally building by building information on the exposures, their height, number of the floor area, materials of construction, and so on. This is the insurance industry has this data in even more detail, but a lot of this data is available now from public sources. So the modeling can be done in much greater detail, looking at building-to-building fire transmission. There's better insurance data. There are changes in the fire service. And by the way, I should point out, in this map, and is this blue line that loops around the downtown. This, by the way, is a map of a portion, the downtown area of Vancouver, British Columbia. And the study that I mentioned, the ICLR study, looked at the entire lower mainland. But focusing in on downtown Vancouver, this blue line is the dedicated fire protection system built by the city of Vancouver to assure fire, water, or firefighting water supply after an earthquake. It is a separate and redundant high-pressure system, separate from the potable drinking water system. I was a seismic consultant on this project, and I compliment the city of Vancouver for doing this. And this is required because this is a map of the potable drinking water system in the city of Vancouver. And the red are the older cast iron water mains, which are very brittle and are quite likely to break. The red lines are the cast iron, the black lines are the ductile iron, and again, the blue line is the dedicated fire protection system, which only protects the downtown area and the Kitsilano and selected higher density areas around False Creek and so on. Again, the red are the cast iron, which are very vulnerable and quite likely to break. And even in areas where there are a lot of black lines showing ductile iron, the breaks in the cast iron system would drain the breaks in the other area. So there's a lot of data here and improved fire following earthquake modeling. So again, this study, it might be time to revisit it. With that, I'll conclude. Thank you very much, and I'm open. Dan, I think, will be refereeing the Q&A. Thank you for your time.
That's right.
Yes.
Great. Thank you very much, Dr. Scawthorn. Very good talk, and we've got a number of questions here. First thing, actually, I should clarify that you pointed out the brochure that we have on our website on WUI fire mitigation at the property scale. I should point out that those recommendations were actually developed by our friends at Fire Smart Canada, Partners in Protection, which is somewhat similar to FireWise in the U.S., and they were kind enough to let us reproduce it to sort of increase awareness in the insurance industry. So no fault on your behalf. It's just I thought I should clarify that for our friends who are on the line here.
Well, we're all on the same team, Dan.
Oh, for sure. First, well, actually, a question since, well, first of all, if attendees have additional questions, please take the time to post them now. But you pointed out several issues related to fire following, that especially the water system vulnerability, and you pointed out the system that Vancouver is developing or has in place. Is this kind of redundant system the only option that's available, or is there anything that we can do with the existing water systems to increase their resistance?
Well, yeah, no, there's a number of things that can be done. First of all, the DFPS, Dedicated Fire Protection System, only protects, as I pointed out, the downtown area and nearby areas. And even within that area, you're still going to have to move water from the hydrants on the DFPS system to where the fire is. And outside of that area, you're going to have to move the water further. So you need what's called large diameter hose, LDH, which is typically a 5-inch hose, or I guess that's 12.5 centimeter hose, diameter hose, and you need a lot of it. So one thing would be to equip the fire service with additional hose and pumps able to draft water out of the Pacific Ocean, which again surrounds Vancouver on 3 sides, or from the Fraser River Delta, or from swimming pools or other bodies of water nearby. With regard to the potable water system, yes, you need to, there's a number of things that can be done. First of all, you need an aggressive campaign to replace the cast iron with more seismically resistant ductile iron or PVC piping. I just came from last night from the national meeting of the American Waterworks Association. There were a number of papers about cities in the United States who are doing this. And the Water Bureau in the city of Vancouver and the surrounding cities have campaigns in this regard, to give them credit. And they are doing this. But they can only replace so many miles a year. It's going to take a lot of time. So they need to step up that campaign as much as they can, as much as resources allow. So those are 2 things. The third thing would be to identify alternative water supply, such as just ponds and lakes in parks, swimming pools, other bodies of water, and then to provide connections that the fire department can quickly connect to those sources. If you have a swimming pool, an Olympic-sized swimming pool, but you have no way from the street to access that water, the fire department's got to somehow run in there with whatever drafting equipment they have, and frankly, it may not be possible, especially if it's inside a building. If you put a fire department connection on the street that allows them to access the water in the pool, that makes all the difference in the world. So this is just 3 examples. I could keep going, but let's move on to the next question.
Great, sure, okay. So during your talk on, or the first part of the presentation on WUI fire and the benefit cost ratios, there are 3 maps that you showed, or 3 specific maps that caught my attention. There was the U.S. Forest Service map that indicated the WUI area, or areas that are considered to be WUI in the U.S. There's the BCR ratio map that was produced as part of that Multi-Hazard Mitigation Council report. And then there was the fire probability map, that's the burn probability map. And so the WUI map from the U.S. Forest Service has a large area in sort of the central eastern part of the country that's considered WUI, right?
Can you see it here?
Yeah, and
Yes.
I think the U.S. Forest Service map, it shows even more concentration or a wider area of homes and structures that are in forested areas. And then when you see the benefit cost ratio map from the Multi-Hazard Mitigation Council report, you see that most of the areas where you have the high BCR it aligns more, I'd say, closely to this map where you have higher burn probabilities. And I suppose the question I'd have is, what are your thoughts about, do you think that, the map with the BCR, high BCR ratios in the West and sort of lower ratios in the central US, would that, do you think, reduce the likelihood that some of the agencies in those central areas would be interested in implementing the WUI Code or related measures? And do you think that's warranted? Should jurisdictions in some of these lower risk areas still be considering the WUI Code, given the fact that they are WUI areas, although at lower risk?
Well, I think if you can see it, I think I'm showing the map you're referring to. And a moment ago, I showed the map of the hazard. This is the map of the BCRs. And they're pretty consistent. So I think that I think the first part of your question was, were there any differences or anything here? And I think the answer is, by and large, they're fairly consistent. The hazard is driving the BCR. If the hazard is low, there's no benefit to mitigating the risk, since the risk is low. And if the hazard is high, the risk will tend to be high, and the benefit cost ratio will therefore be higher. This map is intended for a number of reasons, simply to alert people, but among others to empower or to educate, but education empowers people, to empower legislators to understand that in selected areas it's in everybody's best interest, and so I think that will help the fire agencies there. Outside of those areas, I suppose if you look at the glass half empty, you could say it hurts the efforts of some fire agencies. If it's colored here as a low BCR, and the only thing and yet they still maybe have they think they have a high WUI, or at least want to mitigate it. The only thing I can say is this was a national mapping, and it's not perfect. Nothing is perfect, and it can be improved. And if we zoomed in on one particular county that is colored here low, we may not have had the right data. A more detailed study for that area would obviously be just like getting a custom tailored suit. It'll fit you better. So I hope that answers your question.
Nope, understood. So another related question to the BCR for WUI fire. We have a question from one of our online attendees. So you mentioned that the BCR, the general BCR, sort of applies to all types of buildings. Do you have a sense of how, say, large industrial facilities, oil refineries, and the like perform in terms of both fire following earthquake and wildland fire, say in comparison to typical residential structures?
Okay. All right. So the question asks about larger industrial type, commercial and industrial structures, and then also oil refineries. So in a sense, two different questions. Let me answer the first and then the second. First of all, this BCR and so on was only for single family dwelling. That's the only index building we looked at. The budget had limited resources. We couldn't look at all building types. So this BCR is not meant to be interpreted to a large industrial building or an oil refinery. However, with regard to large industrial buildings, to some extent they have defensible spaces. It's often called parking lots, although you do fill those with fuel called cars once in a while. But large industrial buildings, although they're not wood framed, they burn. And wildland fire transmission to large industrial buildings is is not only not unknown, it's not unusual. And in the 2017 fire up in Santa Rosa, we had Kmart's, which are large big box stores, go up in flames, surrounded by a large parking lot. The embers land on the roof. Fire department can't get to it, and the whole building's gone. So large industrial buildings are, I would say, as a generalization, they are at risk due to WUI fires. Maybe not quite to the same degree as a wood frame structure with no defensible space, or hardly, but still there's risk. Now, with regard to oil refineries, I guess the first question would be, show me an oil refinery in a wildland-urban interface. But with regard, to a fire following earthquake, the record's pretty good. Oil refineries burn after earthquakes. This goes back to the Niigata earthquake, 1964, where the Showa oil refinery burned for 10 days. Marmara earthquake in 1999 in Turkey, where the can't remember the name of the refinery, but that burned. Without a doubt, in my mind, if with a magnitude 7 earthquake on the Hayward Fault, the 5 oil refineries in the San Francisco Bay Area, or with regard to a large earthquake in California, in Southern California, all the oil refineries around the Port of LA and Long Beach, Wilmington, and so on, they're going to burn, without a doubt. They have their own. Some of them have their own fire brigades, but they're not meant for fire after an earthquake, and so on. And also, I should point out, the Hayward results that I presented to you did not. As a matter of fact, I have a page in the report that says this did not look at oil refineries because, again, of project restrictions, budget, and so on. We did not look at it. It's a major concern of mine, and I'm very aware of it, and it's not covered in what we did. And I'd be very interested in looking at it further. Okay.
Thank you very much. I've got a question here from Paul Kovacs, our Executive Director. He is asking, apologies, look at the wrong question. Some large international earthquakes had very extensive fire damage, like the 1906 earthquake in San Francisco, while some other large earthquakes had little or no fire damage. How robust is the evidence about the risk of ignition in conflagration relative to the strength of shaking?
Okay, again, there's 2 questions there. First one, and this is a very common question I get. The first question is, wait a minute, you're showing large losses for fire following earthquake. Where were the big fires in the big China earthquake or the big Pakistan earthquake, and so on and so forth? And the answer is we have different kinds of construction. Fire following earthquake is not, fires follow all earthquakes. They have ignitions in China and in Pakistan or those earthquakes and so on. But the building construction is different, and the fire growth is much less. Basically, the wood frame construction is common in North America, Australia, New Zealand, Northern Europe, and that's about it. Everywhere else, people use earthen materials, meaning adobe, concrete, brick, and so on, to build with. And so the fire growth is just not the same. So the fire following earthquake is a hazard in areas with large amounts of wood frame construction, which is North America, Japan, New Zealand, and so on. We did not have a lot of fires in the New Zealand earthquake of 2000, the Darfur earthquake, and so on, because they don't have a reticulated gas system there. And there was a number of other issues having to do with that. So we can explain why there weren't so many fires in that New Zealand earthquake. So that's the first part. The second part of the question was, how robust or what confidence do we have in the ignition model? The ignition model, I showed there's 2 of them. There's Davidson's and mine. There are others. The Japanese researchers have developed ones for Japan. I'm very familiar with all of this work. They're largely empirical. There have been some analytically based ones where people have tried to literally model the overturning of every lamp and every bookcase in a house and calculate the ignitions. But the best models so far are empirical. There's uncertainty associated with them. but I think that there's no doubt there's going to be fires after earthquakes, and this is the best estimates we have. When we get more data, we'll improve our estimates.
Okay, thanks very much. Well, we're coming up on 2:30 here, so maybe just one last question, and then we'll wrap it up for the day. So another question from Paul, and not to put you on the spot, but it would be interesting to hear your response. Given your experience and knowledge, so you pointed out a couple of the characteristics of your hometown there at the beginning of the presentation. Why did you choose to live in a location with high risk of loss from earthquake and wildfire?
Well, what can I say? There's risks everywhere. I guess I'm close to my job.
Right.
No, there's risks everywhere. I guess the benefits outweigh the risks here. As Paul knows, by the way, I also spend part of the year in Japan and part of the year in Europe. So I'm
right.
I'm hedging my bets.
Right. Okay. Well, thanks again for excellent talk, and I believe we'll be posting the slides and video on our website if anybody else is interested in following up. Before we sign off, any last thoughts?
None from me. I just want to thank Paul and the Institute for the opportunity to speak to the membership here. Great.
Okay, thanks again, and thanks everyone for joining. And that's it for this year, or this season anyway, until September. And so we'll talk to you again.
Thank you.